Okay, and we're going to wrap up Chapter 2 by just slightly addressing the other two forms of thermodynamic cycles. That is, we talked about the power cycle, where the goal is to generate some form of power, and the other ones was refrigeration and heat pumps. Those are the other two cycles that we want to analyze. So a refrigeration system takes energy from a cold body and it puts it into our system. And then we also need to add work into it in order to then reject it to a hot system. So what does that mean? This schematic says it all, but it does not really have practical examples. So let's consider an actual refrigerator. I have a refrigerator and I want to keep that refrigerator cold, and that cold is going to then go into our system, and then having gone into that system, we have to also take work, and that work added to that system, we will eventually reject the heat to the hot source, which is our ambient conditions of the kitchen. So the work is the net energy transferred to the system, and by this direction, we have that the work will be negative because we are adding work to the system. Our Qin in this situation is the cold body. This is our Qin, and this is our Q out that we have. Our form of work is now the Q out minus the Q in. Note, for the power cycle, we had the Q in minus the Q out. But in this situation, we have the Q out minus the Q in. Therefore, the work that we have for our refrigeration cycle will be negative. The efficiency, or in this situation, our coefficient of performance, beta, that we are using for a refrigeration cycle is defined as the Qin. Once again, what is the Qin? It is the amount of heat that is being transferred from your refrigerator or the ice box into your system relative to the amount of energy that you also have to add to the system. A heat pump is the exact same thing as a refrigerator. It's just that the target has changed. In the refrigerator, we wanted to keep the cold body cold. But in a heat pump, we want to keep the hot body hot. So our goal, what is it that we want, is different. This is like putting the refrigerator outside and opening the door, and therefore we have the outside air, which is already cold, and to that we add work into it to run the compressor. And that work energy plus the amount of energy that we have from the Q outside will be then deposited into this heated air. That's our target that we want. So thermodynamically, what we are saying is that our target is now the Q out. That is our target rather than the Q in. The way that we determine the amount of work required is the same as the way that we had determined the work required for a refrigeration system. However, the coefficient of performance is different. It is the Q out divided by the work that we had to put into it, rather than the Q in divided by the work of the cycle for the refrigerator. Let's take a look at this example. We've got a heat pump cycle. It will deliver 900 kilojoules of energy into the dwelling, which is currently at 20 degrees. It will receive 600 kilojoules of heat from the outside air, which might be at a much colder 5 degrees C. We know that the work is going to be the Q out minus the Q in, and that will be 300 kilojoules. Therefore, the 300 kilojoules from the work that we had to supply by plugging it into the wall, plus the 600 kilojoules from our outside cold air at 5 degrees, will deposit a total of 900 kilojoules into the living environment. And the coefficient of performance in this situation will be equal to our heat that gets deposited into the dwelling relative to the amount of heat that we had to add in, and therefore that would give us a coefficient of performance of 3. Note that the coefficient of performance can be greater than 1 by its definition.